Hey, BChem, welcome to Unit 4. We are going to be getting into talking about solutions now. And what we're going to actually be doing is tying together our work with Unit 3, which was chemical composition and stoichiometry, with solutions. So if you said to yourself, you know what I've been missing in my life is doing stoichiometry with molarity, that's going to happen in Unit 4 here. And so today what we're going to be doing is we're going to be reviewing how solutions kind of are formed in the first place. We talked about it when we talked about polarity, but I want to review with you kind of what happens when we talk about ionic and covalent solids, and then we're going to get into measuring concentration and doing those calculations. So just as a little bit of a review for you, when we take a covalent compound and we try to dissolve it in water, and I'm going to be talking mostly about water in this unit because it's very rare that you find a solution that you're going to actually do in lab that doesn't contain water, and all the ones that we're going to do also contain water. So we're going to use that as our solvent for basically everything from this point on. So anyways, what happens is when a covalent solid dissolves, what's going to happen is they're going to break up into their individual molecules. Now, a covalent solid is one that's made up of all of our nonmetals. Typically, we're going to see things like carbons and nitrogens and hydrogens and oxygens and sulfurs in those compounds, and no metals when we see them. So an example of this would be like table sugar, which is called sucrose. So sucrose has kind of a ringed structure that you're kind of seeing here in the picture. This is obviously not the correct Lewis diagram of this, but the chemical formula for sugar or sucrose is C12H22O11. So it's very much a covalent compound. Everything is within that under kind of 1.9 difference in electronegativity. So what ends up happening is that when we think about their lattice has individual molecules at the intersection points of the lattice. And so when water goes in and dissolves covalent solid like sugar, what it does is it surrounds itself, if it has polar points, by those polar points, and it pulls the whole molecule apart. So it doesn't break up into individual carbons and hydrogens and oxygens. It just breaks up into whole C12H22O11 molecules, and then they float around individually, kind of surrounded by water. In contrast, when I have an ionic solid, and I'm sorry, this is kind of off here a little bit. So this should be ionic, not covalent. What happens when I have an ionic solid is that they break into their individual ions. So obviously I had a little error on here, but you guys can fix it. So a covalent compound breaks up into molecules. An ionic compound is going to break up into its separate ions. We talked a lot about the ionic lattice and how we have individual ions that are attracted to each other. And so when we are talking about an ionic solid dissolving in water, the waters attack the individual ions, oriented either with the positive or negative end of the molecule to the appropriate side, and they break apart. So what that means is if I have something, let's say like calcium chloride here, that's CaCl2, when I have one molecule of calcium chloride that breaks apart, I get one calcium 2 plus ion, and then additionally 2 Cl minuses. So when we talk about dissolving compounds that are ionic, you have to be really cognizant of the charge of the ions as they break apart. So again, in this case, it's one calcium 2 plus and then 2 chlorine minuses, or what we call the chloride ions. Each chloride has its own oxidation number of -1, and it takes 2 of them to neutralize or cancel out that calcium. Just kind of similarly with ammonium carbonate, when ammonium carbonate would break up, and this is an ionic compound because it's 2 polyatomic ions coming together. When these break apart, they break into their individual ions as well. And so I have, in this case, because of the subscriptive 2 down here, 2 ammoniums, which are NH4 pluses floating around. So it's the whole cluster of ammonium and its positive charge that leave that ionic lattice. And the same thing with the carbonate. It's one whole CO3 cluster with a -2 charge. They are potentially going to ask you to draw these and acknowledge the ions that form. So please be very careful about this. It is not going to be two NH4s stuck together as a +2 moving around. It's two separate ammoniums, each at a +1. So just be aware of that as you go along, because this has consequences for calculations for concentration. When we talk about concentration in science can be expressed in a bunch of different ways. The one that we're going to talk about and that we use, I think, and it's honestly the most descriptive and useful for us, is something called the molarity, which we'll get into in just a minute. But there are also calculations that you will see where they discuss something called molality. There is the percent calculation, and biology, not wanting to knock them, but definitely going to. I think, don't like using the mole idea and doing that math. So they do percents, kind of like percent composition. So they talk about a solution being a 10% solution, which means that 10% of it by mass or by volume, depending on what you're talking about, is going to be solute versus the solvent. I think it's kind of a slacker way to do it, but I don't want to get into a beef with your life science teacher. So we'll keep that quiet. And then there's something also called the normality that you will use with acids once in a while, but we are not going to worry about that. So the big one we're going to be talking about is molarity. When we talk about molarity is always calculated as moles of solute over liters of solution. So you need to know, if you have information about your solution, you need to know how many moles of that solute you have, and you need to know the total combined volume of your solute and your solvent. So like, for instance, if it says you take some solute and you add it into 100 milliliters of water, you don't know what the volume of those two things combined is going to be. So when we're doing calculations, we have to talk about the total combined volume in liters, not just the amount of water that we're adding to it. And when we talk about molarity, you're going to see it in a couple different ways. You'll see it expressed as capital M, moles over liters, and molar, and they all mean the same thing. And you have to be very careful when you do these calculations, because this is a ratio. Units get messy when we're talking about things further on. And when we get into doing calculations on how to actually make a solution, I'm going to be kind of all over you about that. And just as a reminder to you, because we have liters here in the denominator, oftentimes you don't make an entire liter of solution. So you're going to have to convert from liters to milliliters and back and forth pretty comfortably. 1 liter is equal to 1,000 milliliters. So just kind of keep that in mind and be careful when you convert, because it's a stupid way to kind of lose points. When we talk about solution concentrations, you cannot be talking about pure solids and pure liquids. So what I mean by that is, if I have a sample of pure gold, regardless of the volume I have, the number of moles in that volume is always going to be the same, because it's a pure substance. So my sample of gold is a pure sample of gold. It's all gold, so it has the same molarity no matter how much you have of it. When we talk about liquids, pure liquids specifically, it's also the same thing. So if I have 3 different volumes of water, I am going to have the same number or the same moles per liter, because it's a pure substance. However, when we talk about gases and we talk about solutions or aqueous things, you can have different molarities, because you can fit more chemical inside a particular unit volume. So if we're talking about a gas, we have this container of a gas, you can put more moles into that container. And the same thing with your aqueous solutions, because you have this, water that can potentially take more chemical, whereas pure chemicals, you just can't do that. Okay, so we're going to go through an example calculation, and we're going to see how you do with this. So my first question for part A is, what is the concentration of a 450 milliliter solution that contains 200 grams of iron 2 chloride, which is FeCl2? What is the chloride concentration of the solution? So that's question B. Okay, so if you want, you can pause this video and give this a try on your own. I'm going to work the problem out in this same video, so you don't have to go to another one, and then we'll see how things go. So if you want to give it a try, go ahead. You can pause the video and we will work it out. Okay, so FeCl2 in 450 milliliters of solution. So when I look at a solution problem, the biggest thing that I do is I try to identify what type of compound I have. Do I have an ionic compound or a covalent compound? And it might not be necessary for the problem, but I always try to kind of give myself a mental picture kind of when I'm going through this. So I'm going to have some number of moles here in the FeCl2, and I'm going to try to divide them in a total volume of 450 milliliters. FeCl is an ionic compound because it has a metal and a nonmetal. So when this thing dissolves in water, okay, I'm going to get 1 Fe plus 2, and I totally did not make enough room for that, and 2 Cl minuses. Really need to work on writing bigger. There we go. Okay, so I'm going to get 1 iron 2 plus ion and then 2 chloride ions every time that this thing dissolves. And again, you don't need to draw this picture, but I would try to make a mental picture of what's happening as you're going along with this. Okay, so I need to get, we know for our molarity calculation, it needs to be moles of my solute divided by the liters of solution. Okay, so moles of solute divided by liters of solution. So my solute is going to be the FeCl2, and I currently have that in grams. So I need to convert that into moles to make that work. So that's what I'm going to do first. 200 grams of FeCl2, and then I need to convert that into moles. So I've got to get out the old periodic table. I'm going to find Fe. Fe is 55.85. I'm going to add that to 2 chlorines, which are 35.45. And when I do that, I get a molar mass of 126.75. I want to convert that to moles, so I'm going to put the molar mass on the bottom, 126.75 grams for every 1 mole of FeCl2. Okay? If I do this math, I'm going to take 200 divided by 126.75. I end up getting 1.58 moles of FeCl2. Okay, so I've got my moles. If I want to figure out my molarity, I'm going to move this because it's kind of icky. It's just running out of room here. So if I've got 1.5 moles of FeCl and I know the volume of the solution here, I can do my conversion. Now, you do not need to show the work to convert this to liters, but I'm going to show you because I think some of you may forget. So it's 450 milliliters. And then for every 1 liter, I have 1,000 milliliters. I know that in one of the problems that we did previously, I saw some of you guys had this flipped around. So just please make sure that you're very careful with that. And that means I have 0.45 liters. So I'm going to put that 0.45 liters in my denominator here. And if I take 1.58 and divide it by 4.5, I end up getting 3.51 molar FeCl2. So that's the concentration of the iron chloride solution. The second calculation asks you what's the concentration of the chloride ion though. So if you think about it, if I drop a mole of FeCl2 into this beaker, I'm going to get, in theory, 1 mole of iron 2 plus ions and twice as many chloride ions. And so to represent that for part B with the calculation, I can take my concentration of FeCl2, 3.51 molar, and then I can actually set up kind of like a mole ratio. So for every 1 mole of FeCl2, I am going to get 2 moles of Cl minus. And so when I do that, I get right in the neighborhood of 7, so it's 7.02 molar Cl minus ions or chloride ions. So when we do those types of calculations, you have to take into account how many ions are formed in this situation, okay? When you see compounds in actual labs, there's just something I want to kind of point out to you. Like, for instance, the FeCl2 compound here. FeCl2, when I get it, like from the company, comes as a tetrahydrated compound. So it comes in as FeCl2, and then there's 4 waters attached to it. So when this substance dissolves into water, it still makes this solution, because any of the H2Os that are attached, all they do is kind of fall into the background here. And then this is assumed to kind of all be H2O in the background. Okay. Now, they are not going to ask you to draw water molecules in here if you are doing a diagram on a large scale. However, sometimes if they're asking you how something specifically dissolves, you do need to be cognizant of the fact that they are going to sometimes ask you to draw the waters in. So you draw the waters in when they tell you to. Otherwise, we are going to assume that this is here. So if we're going to be talking about like a chemical reaction that needs a beaker drawing, you wouldn't need to draw the water in. But if we're drawing the dissolving process of that one individual solution, I would definitely draw the water in then. And we'll practice that a little bit more. Okay? So if you don't have any questions, your first part of your homework is going to be to do calculations kind of like these and take a look at some drawings. Okay? So if you have any questions, you should come to a meet and get things cleared up. Otherwise, good luck.